say that okay, so I did I thought I did a recording, but apparently I didn't actually press the button to record. So I guess I'm going to go through the solution of this daily problem. A little unfortunate because I think it'd probably be easier if I had the process work, but anyways. The problem here is minimum difference in sums after removal of elements. You're given a zero index array of 3 times n elements, so n is like a third of the length of the array, and the array is exactly a multiple of 3. You're going to be able to remove basically a third of the array, any subsequence of elements that has of n elements from it, and therefore you have 2/3 left. And if you divide the 2/3 into the first half and the second half, the sum of the first half and the sum of the second half, you're trying to find the difference in their sum and trying to find the smallest possible difference. So as an example, if I have a array 312, there's 3 elements, and in this case would be 1 because 3n is the length of the array, which is 3. So basically if I delete any one element and split the remaining elements as first half, second half, what is the smallest possible difference between those? In this case, if you delete the 3, you get 1 minus 2, which is -1. If you delete the 1, you get 3 minus 2, which is 1. If you delete the 2, it's 3 minus 1, which is 2. So the smallest difference there was -1. On the second one here, there's 6 elements, so each third would be 2 elements. So the best possible deletion would be the 9 and 1, which leaves 7, 5, 8, 3. 7, 5 is the first kind of third. 7, 5 adds up to 12. 8, 3 is the second third, which is going to be 11. And then 12 minus 11 is going to be 1. And that's the smallest possible. So going over kind of the explanation that I had that is lost in time originally. So the main idea would be if you were to think of the array as, let's say you label the array as A, B, or D. A is kind of your first half elements, B is kind of your second half elements, and D is your kind of delete elements. So let's say there's 6 elements. It could be something like AD, AD, BB, or it could be something like AA, DD, BB, or it could be something like, you can make up your own kind of sequencing, but you'll note that anytime or any way that you kind of structure the deletion and the things that are left over for the first and second half, there's a separation between the latest element of A and the earliest element of B, in the sense that A and B are always kind of before and after each other. You're never going to see a BA in any fashion. And in particular, if you think about where the last A occurs, the last A occurs, if you know where that is, then you and you know exactly how many A's there are, right? There's going to be n A's and there n B's. If you have a certain index where that occurs, you can subtract n from that index, roughly, and you have the number of deletions, number of elements that must be deleted before that index. So if like this is index 3 and you know that there's 2 A's, then there's like 1 deletion. Similarly, if this was index 4 and you know there's 2 A's, then there had to be 2 deletions. So kind of in written description that for any index where that divides where A and B's are, where the A are the elements in the first remaining third and B's elements in the B's are the elements in the second remaining third, it can determine how many elements are deleted before that index and after that index. So as another example, if you have an array of 300, so n is like 100, right? If you have a dividing index, let's say the last A occurs at 175, that means that within the first 175 elements, there had to be 100 A's and 75 things that you delete. And then within the last 125 elements of that 300, there had to be 100 B's and 25 things that you delete. So 75 elements are deleted in the first 175 and 25 elements are deleted in the last 175. And why that kind of helps with the calculation would be if you think about what is being deleted in order to kind of get the smallest difference. The smallest difference occurs when the first sum is as small as possible and the second sum is as big as possible. And if you want the first sum to be as small as possible, the first k elements to be as small as possible, then you want to delete the largest elements of that. So whatever elements are there, like of this 175, you can delete the biggest 75 in order to keep the smallest 100 to be your sum of the first A elements, right? The sum of A elements. Similarly, if you want to do the second half, you're going to delete the biggest elements to be from the second half in order to have the you want to do the smallest element from the second half in order to make the sum to be biggest if possible. And the way that you would want to easily identify the smallest 100 elements or the biggest 100 elements to keep would be using heaps. A heap would, if you add elements to the heap and remove elements from the heap, always kind of keeping the heap the same size, then the heap would always be like tracking the smallest elements, the smallest 100 elements. So going over the main algorithm here, you get the value of n. I created so if I wanted to work on the first portion, then I'm going to start with an empty array of size n, or size 3n, I guess. And then I'll start by tracking the first n elements to be part of the heap. So that's this thing. Since I know that when I'm working with the first elements and I want to I'm going to try to keep the smallest 100 elements in the heap and always kind of remove the biggest element from it. And if I want to remove elements from the heap in Python, it always has to be the smallest element from the heap. So the way that works would be you add the negative of the element to the heap, and then you remove the biggest, or you remove the smallest value from the heap, which is the smallest negative, which ends up being the biggest value, biggest positive. So yeah, so this code right here. And then I have an array of sums, and as I iterate over the possible indices where the last A occurs, where the last A is the last element of the smallest third, which has to be at least an at index n. It can't be index before n because then you don't have enough elements, and it can't be after index 2n because you don't have enough elements that way. Like there has to be n elements that you keep and n elements that you delete, or there has to be exactly n elements that you keep and at most n elements that you delete. So so for all the possible indices where you're kind of dealing with that, you take the value, add that value to the sum, to the current sum. You add that value to the heap, and then you remove the biggest element value from the heap, keeping kind of the negatives involved here in order to make things work. And then you remove that biggest value from the current sum, so you subtract it out. And then you store that current sum to the array at that index. So to be clear here, what early array ends up storing is for every valid index where you can have the last element in your first third that you're keeping, it's going to store the sum of the smallest sum of the values that you want to keep. So for instance, in the second example, the size is 6, so you're keeping 2 elements for your first third and 2 elements for your last third, right? So the sum of the things that you would keep starting at the earliest thing that you would possibly start at, which is the second kind of spot, you keep the 7, 9. And then the next spot would be of the first 3 elements, you're going to keep the smallest 2, so it'd be 7, 5, so it adds up to 12. So that's 12 there. And then the next, at the next spot in the array, if you want to keep the smallest 2 of the first 4 elements, that'd be 7, 5, which is 12. So the process of that is like you initially have some sum, like 16, and then the next thing that you do is and that 7, 9 is your heap. You add 5 onto the heap, so it becomes 7, 9, 5. You remove the biggest element from the heap, which is the 9. And when you remove that 9 from the heap, you remove that from the sum. So like 7, 9 is 16 plus 5 is 21. And then you remove the 9, which is 12. You store the 12 there. And the next step is, you have an 8. 8 adds to 12, which is 20. And then you remove the smallest, or the biggest element from the heap, which is 8, so it becomes 12. So that's this portion here. Have your value, add that value to your current sum, add that value to the heap, move from the heap the biggest value, and deduct that value from the sum, and then store that to the array. And then you do the same kind of process in reverse for the later heap. So you're tracking, or I'm tracking the sum of the last n elements. So that's this thing, or later heap starts with the last n elements. So starting from index 2n to the end. Calculate the sum of those elements, and then you iterate over the indices, where at each indices you take the value, add that value to the sum, you push that value to the heap and pop the smallest value from the heap, remove the smallest value from the sum, and then you store that value from, you store that sum into your array. So if I were to print out the later array here, this would be like you're starting backwards here. Your later heap would have 1, 3. The sum of those things is 4. So that's the first thing that you have at that index. And then as you iterate backwards, 8 is added to the heap, 8 is added to the sum. So 4 plus 8 is 12. And then because your later heap wants to keep the largest values, it's going to remove the smallest thing. So it's going to remove the 1. And then 12 minus 1 is 11. That's what you store. And then you iterate once more. 5 gets added onto the heap. 5 gets added onto the sum, so 16. Smallest element gets removed from the heap, which is 3. So 16 minus 3 is 13. So again, this is basically the sum of the smallest n elements after this index. is what this represents. And then once you have those two components, you can just kind of iterate over the indices and then subtract the kind of sum of the smallest n elements before this index minus the sum of the biggest n elements after this index, right? Just because of the way I set up, there's a bit of offsetting that I have to do. So it's like you're comparing the 16 with 13, the 12 versus 11, the 12 versus the 4. And the smallest difference is 12 minus 11. Here was like 3, 2, 1, 2. And the smallest difference was 1 minus 2, which is negative 1. All right. Yeah. That's that. I'm not sure how long this explanation is, but it took me like an hour to do the code prior, so it's pretty fast going through this. So the summary, that's the overall concept. You're going to create, what I did was create a array to handle the first third, where the array is, again, supposed to store the sum of the n smallest elements up to index k, where k is an index that's kind of valid, n to 2n. And then in order to create that array, or to store the sums in the array, you need to have a variable for the current sum and then a variable for the heap. And then while iterating over the indices, add the value to heap, add the value to the sum, move the largest value from the heap, subtract the largest value from the current sum, store the sum into the array. And then very similar process for the back half. And then find the difference of those corresponding sums in those arrays. Time complexity, this was going to be O of n log n, where n is a third of the size of the array. Heaps generally have an insertion cost of log k, constant removal cost. And so if you're inserting n elements, then it's going to be n log n. And note here that the size of the heap is constant pretty much, or it's always 1/3 the size of the array. So if your array is 100 or your array is 300, then the heaps that you're tracking to keep track of the smallest 100 or the biggest 100 is always 100 size. So you're always adding on to the heap, which is always log 100. And then you have another 100 times doing that. Space complexity is O of n, where n is the size of the arrays that you're keeping track of the sums, or size of the heaps that you're keeping track of the smallest or